Let's take a look at how to solve a conduction problem in ANSYS. And while doing so, to understand what's happening under the black box, we will invoke the concepts that we looked at in the big ideas in finite element analysis, where we're looking at one-dimensional heat conduction. Here, we have two-dimensional or 2D heat conduction, so temperature varies in two directions, x and y. And we'll say the conduction is steady, so there's no variation with time. And we have a block, and we are given the boundary value problem here, okay, corresponding to this 2D steady heat conduction. This equation here, which is called the Laplace's equation, represents the energy conservation. And this is in the absence of heat generation. There's no heat generation here. And theta is a dimensionless temperature. So you take the temperature and you non-dimensionalize it this way. So T naught here in the non-dimensionalization is the constant temperature of the bottom face. Okay, so it's the temperature at which you maintain that face. And T infinity is the far temperature of the fluid bathing the right face. So this face is exposed to fluid, and if you move far enough away from that face, you have some temperature for the fluid, and that's what that temperature is. So those are the two temperatures used in the non-dimensionalization. And in terms of the boundary conditions, here T is equal to T naught, so theta is 1. And that's called an isothermal boundary condition. It's just setting the temperature. Here we have, it's setting the heat flux to be 0. It's because the heat flux in the 2D, okay, it's if you need to take heat flux is a vector, and this will give you the heat flux. This will be proportional to the heat flux in the x direction, and that's perpendicular to the face, and so that's set to 0. And here the we want the heat flux in the y direction to be 0, and so that derivative is set to 0. This is also same as that. Both of these are heat flux being set to 0. And this is a convection boundary condition. And here BI is the BO number, so this gives you the aspect ratio, that it's the block is twice as high as wide, and this is called the BO number, and it's a non-dimensional way to express the convection coefficient. And the convection coefficient gives you a measure of how much heat is being exchanged between the block and the fluid. So for instance, if our fluid was air and we put a fan and we blew the air, we would have more heat transfer happening between the two, and we would represent that by a higher value of H. And this problem shows you the three major boundary conditions you get in a conduction problem: isothermal, convection, and heat flux. So we'll find the temperature and heat flux distribution in the block using ANSYS. The solver will find the nodal temperatures using a procedure similar to what we saw in the big ideas in FEA. So it'll go from the boundary value problem to a system of algebraic equations in the nodal temperatures. And it'll do that using the piecewise polynomial approximation for T that I just talked about. And each algebraic equation will relate a nodal temperature to its neighbors. For instance, if I consider this particular node, when the solver derives the algebraic equation for that node, it'll relate this node to its, the nodal temperature let's say if this is 3, it'll relate T3 to the neighboring temperature values. And to see which temperatures will be related, we can use a principle that I discussed in the big ideas. So you look at all the elements that are attached to that particular node. So we have 4 elements attached to that node. And then you pick out all the nodes that are attached to each of those elements. So this element is attached to these 4 nodes. This element is attached to these 4 nodes. And then you have these nodes coming in and these nodes. Which means that the algebraic equation at this node will relate T3 to these other values. This node is not connected to this element, so for instance, those nodes won't be involved in writing that relationship. And we also know that there's going to be a constant term that comes from heat generation. In this case, we don't have heat generation, so there won't be, the algebraic equations won't contain at this node. The algebraic equation at this node won't contain the any constant term. And once the solver generates those algebraic equations, in fact, it will, it thinks of it in the matrix form. The temperature vector, for instance, in this case will be, you have 16 temperature values. So this will be a vector with 16 rows in one column. The stiffness matrix will be a 16 by 16 matrix, and so on. And similarly, you can think about what's the dimension of Q. And it will invert that, so that's a matrix inversion problem, and determine the nodal temperatures. So you'll have the 16 nodal temperatures, and everything else is calculated from those nodal temperatures through post-processing. So for instance, you can find the temperature at any location through the interpolation from the nodal temperatures, and then you differentiate that, you can get the heat flux. And the heart of the method is going from the differential equations to a system of algebraic equations. Let's think about how the process that we discussed in the big ideas in FEA gets extended to this to the 2D case. How to derive the system of algebraic equations? We have our piecewise polynomial approximation for the temperature. That's an assumed shape that's constructed element by element. And if we plug it into the differential equation, we won't get our algebraic equations as we saw in the 1D case. The same thing applies in the 2D. So we go to the weighted integral form, where we multiply the differential equation with a weight and integrate over the entire domain. Now it's an area integral, so it becomes more complicated. And we know from the 1D discussion that we cannot satisfy this for any arbitrary weighting function because we've assumed a shape for t. So what we'll do is we'll satisfy it for a weighting function for which we pick a shape. So we pick a shape for t, element by element. We pick a shape for w, and then integrate over the domain. And then if we input, if we plug in the piecewise polynomial approximation for t and for w, out will pop the system of algebraic equations in nodal temperatures. And the key trick, if you remember, is to do integration by parts and transfer the second one of the derivatives to the weighting function. So you'll go to a first derivative in temperature, and you'll go to the first derivative in the weighting function. That works in 1D, that works in 2D also. The details get more complicated, but they are implemented in the ANSYS solver. Let's move to the third aspect of pre-analysis, hand calculations of expected results and trends. So we now know what's a mathematical model we want to solve. We've talked about the numerical solution strategy that ANSYS will use. We will look at post-processing in ANSYS, so let's move our attention to hand calculations. And in this particular case, this mathematical model that we have has an exact solution. So the we have an exact solution. We can solve the mathematical model exactly, and we can compare our numerical results to that exact solution of the same mathematical model. Before I talk about the analytical solution, let's think about the trends. Okay, so I'm going to think about trends, and in most problems you're not going to have an analytical solution, which is why you're turning to ANSYS and the numerical solution technique. But you can always think about the trends, and that's going to be your hypothesis of what's going to come out of the solution. That's very important to do. One thing we can work out is what is the direction of the heat flow at the boundaries. And you can do this for any heat transfer problem. And in our case, the BO number is 5. We have W equal to 1 and K equal to 1. So essentially, we are setting the convection coefficient to be H to be 5. And you're going to get, significant convection between the block and the fluid. When I present this in class at Cornell, I ask students to take a few minutes and work out, the direction of the heat flow at the boundaries. And I'll give you a clue. The heat flow in any direction is proportional to the temperature gradient in that direction. If I come to this boundary, there's no temperature gradient in the x direction, so I can't have any heat flow in that direction. Okay, so Qx has to be 0. Using that clue, you can work out what is the temperature, whether you can have heat flow in that direction, tangential direction, and the normal direction at each of these boundaries. And you can confirm your hypothesis from what you get in ANSYS. So at this point, you might want to pause the video and kind of sketch that out on a piece of paper. And the analytical solution to our mathematical model, I'll show you, and this is courtesy Professor Michel Luge, who presents this in his class when he teaches the heat transfer course in mechanical engineering at Cornell. The analytical solution is found using separation of variables, and it comes out to be in the form of an infinite series. And this is a constant, okay? So these are constants that depend on these eigenvalues, and in a moment I'll indicate how you find those eigenvalues. And it's going to depend on the BO number, and it's going to depend on the aspect ratio. And the BO number and the aspect ratio are inputs into the problem. And these functions are eigensolutions, and they have a cosine variation in the x direction, and then they have this kind of variation in the y direction. So it's a product of the x variation and the y variation. And the eigenvalues satisfy this nonlinear so-called transcendental equation. And the textbook that is used at Cornell, and this is probably true of other heat transfer textbooks, they tabulate the values of lambdas for different values of the BI. So you can find the lambdas, and you can find theta at, say, you want to find the temperature at any x and y. So you have x and y, so you can find theta, you can find f, but you have to do this for each eigenvalue. And then you have to sum over the series, and you would use kind of a finite number of terms. This is a relatively simple problem. In fact, for somebody who knows ANSYS, this problem is a piece of cake. And the analytical solution is fairly complicated, and then it has restrictions on the boundary conditions and also on the geometry, because you can't extend it to any geometric shape. Whereas the ANSYS solution methodology is not restricted by the geometry shape or by boundary conditions. So that kind of gives you an idea of the power of having a tool like ANSYS at your disposal. Let's do the pre-analysis before we get into ANSYS. And the first thing we will do is we will take a look at the mathematical model that we need to input into ANSYS, and then we'll go on to consider the numerical solution strategy used by ANSYS to solve that mathematical model. The mathematical model is a boundary value problem, and we are given the non-dimensional version of that boundary value problem, which I discussed before. We have to input a dimensional boundary value problem in ANSYS. and this has to correspond to the non-dimensional boundary value problem. And here's a dimensional boundary value problem we will input into ANSYS. And what I did was I worked out the corresponding inputs in ANSYS such that this problem would look exactly like that problem. First, let's take a look at the governing equation. This looks the same, and I can set any value of k, and essentially those two equations are the same. And this is energy conservation in the absence of heat generation. This boundary is easy. I just set it to 1, just like over here. This boundary is easy. I just set insulated. So instead of d theta by dx, I'm setting dt dx. Similarly over here. Okay, so there is a correspondence between that boundary condition and that boundary condition. Now this boundary condition is a little bit more tricky. So I will set k equal to 1. So here I'll set k equal to 1 watts per meter per degree Celsius. Then the left-hand side here looks like that. And the right-hand side I will set h equal to the BO number that I'm given, and I'll set the temperature of the fluid to be 0 degrees Celsius. When I do that, this boundary condition looks exactly the same as that, and then this dimensional boundary value problem looks exactly like the non-dimensional boundary value problem. And ANSYS will report the temperature in degrees Celsius, but I can interpret that as a non-dimensional temperature theta. Okay, so T and theta will be the same if we do that. So that's a trick to solve that non-dimensional problem in ANSYS. Let's consider how the ANSYS solver will solve our mathematical model for us using the finite element method. And in this discussion, I will invoke concepts that we looked at in the big ideas in FEA. So I'm moving from talking about the mathematical model. So we know that our mathematical model is a boundary value problem. So I'm moving from talking about that to talking about the numerical solution strategy. So we have to divide the domain into elements and nodes. So we have a rectangular domain here, and we divide it into 9 little chunks. Each little chunk is called an element. So here I've highlighted one element. And the corners would be, I would call them the nodes. So I'll say these are the nodes. By the way, when we are in the ANSYS solver, it will also put in the mid-side nodes. We'll get to that when we are in ANSYS. For now, let's think of the nodes as just the corners of each element. And then we reduce the problem to determining temperature only at the nodes. Here I have 16 nodes, 4 times, 4 rows of these. So I have 16 nodes. So I'm going from determining temperature everywhere, so needing to determine a 2-dimensional function, to determining 16 temperature values. And that's a big simplification, and that's the advantage of discretization. And to use polynomial interpolation to relate temperature within an element to the nodal temperatures. If I want to know what's the temperature there, I would interpolate between these 4 values. In the 1D case, we were interpolating along a line. Now we have to interpolate within an area. So the interpolation is more complicated. It'll be a bilinear interpolation in this case, but the idea is the same. I think of this as, this value is a weighted average of these 4 values. And the weights for each of these values is given by the so-called shape function, for those of you who have seen shape functions. And now that we know that we need to determine only a discrete number of values, let's think about how the solver will determine those discrete values of temperature. How to reduce the error in the finite element solution. As we saw in the big ideas, the finite element solution tends to the exact solution as the polynomial approximation gets better. Two ways to do this. First is to increase the number of elements. This is, I think, intuitive to most of us. If this is our original mesh, we can refine the mesh. We can use twice the number of divisions in each direction. So we'll go from 9 elements to 36 elements. You'll have 4 times the number, which means that you're representing the temperature field now as a superposition of 36 polynomials, whereas over here it's superposition or combination of 9 polynomials. So clearly, dividing it into 36 polynomials is better than dividing it into 9, using 9 polynomials. The other way is to increase the order of the polynomial within each element, and you do this by using more nodes per element. In fact, the answer solver, as we will see, will do that. It'll calculate the temperature not only at these locations, but also at the mid-side nodes. So if you want the temperature here, it's calculated as a weighted average of these 8 values. So you have 3 plus 3 plus 2, 8 values, and which means you have a second order interpolation, right? You can so in this direction you can write a second order interpolation. In this direction you can write a second order interpolation. So you have second order interpolation in both directions, and that will give us a better solution. So in this case it'll be 9 second order polynomials rather than 9 first order polynomials. Okay, so those are the 2 ways in which we can reduce the error, and really because the solver already uses the higher order element, we'll have to worry about refining, using more elements. We also, as we get to more complicated shapes, we also have to worry about the element shape, and we'll see that in the bike crank example later. Let me show you a couple of ways to save the project. And you can go to File and click on Save, and that's what you need to do. I already did that, so it already has a name, so I'll select File, Save As, and that should, and you should see something like this menu where it's prompting you where you want to save it. And I created a folder called Answers Files, and I'll give it an appropriate name, so I'll say 2D underscore Conduction. I was kicking and screaming from Linux to Windows, so I tend to put in underscores because you couldn't use spaces for file names in Linux. Okay, when I do that, and now if I go to that folder, okay, I see there is this WBPJ file, and then there's this folder underscore files, and this is a folder, and if you go in, you see it has a bunch of other folders and so on, and then this backup will go away when you save and exit the project. And you need to save both the WBPJ file and the this folder. I've seen students tripping up because they have saved only the WBPJ file, and that way you cannot retrieve the project, and no amount of cursing and screaming at the software will solve the issue. Now there's another way you can save it, and that is you can say File, Archive, and then this saves it in the WBPZ format. So I'll say Save, and it says, do you want to save results? I don't have results. The only reason you would deselect that is if you had a big model and you didn't want to save, the nodal temperatures in the big model. So you'll get a compact. If you deselect this, you will get a compact file that you can email to a somebody in your cohort or your colleague and so on. In this case, we can leave that on. And if you have imported files, it's also a good thing to select that unless you want to save on space to share it with somebody else. Now, if you don't save the result, what happens is, when you retrieve the project, it'll say, hey, you have to regenerate the results, and you can do that just by right-clicking on solution in the solution in the finite element interface, the answers mechanical. So don't worry about that now. So I'll select both of those and I'll say archive. And then if I go back to my folder, I see that I should have a single file. So it zips it all, and then I just need this one file. And in this case, it's 50 kilobytes. And I can just email that one file, for instance. And to bring that project back up, you can just, double click on it. Or within this interface, you'll have to say File, Restore Archive, and then you see you can read in WBPZ. And when you do that, it'll ask you to save it in the conventional format. And so that's a couple of ways in which you can save the project, and you have to be a little bit careful. I've seen students, saving things to a flash drive and then running answers from a flash drive or a USB drive. And that tends to be very slow. So what I would recommend is that you save, you move things to a local drive, say the desktop, you run things from the desktop, and then once you are done, exit answers, and then you can drag things onto and save things onto your USB drive. In the geometry step, we will specify a key aspect of our mathematical model, namely the domain over which we want to solve the governing equations. And once we have the domain, we can specify boundary conditions at the edges of the domain. As we saw in pre-analysis, the domain in our case is a rectangle, so we need to input a rectangle into answers. Before I show you how to do that in answers, I want to make a note about version differences as the years go by. This is a hands-on course where you're learning the fundamentals of finite element analysis as well as its applications by working through problems in the selected finite element tool, in our case, answers. And I think there's great value in learning by solving problems with an expert guiding you. However, the challenge of this kind of a hands-on course is that the version of the software, answers in our case, changes. Let me talk more about that by going to my slide. The current answers version is 18.2, and that's the version we are recommending for the 2018 edition of my MOOC on EDX. This module, the 2D conduction module, was originally created using version 16.2, and that was just over a year ago. And you can see that in that time, the current version has gone to 18.2. And at that time, in version 16.2, Design Modeler was the only geometry engine, so I recorded videos showing how to create that rectangle in Design Modeler. Currently, in version 18.2, there is a new geometry engine, SpaceClaim, which is the default geometry engine. SpaceClaim is a powerful tool for computer-aided design. It was originally developed by a company called SpaceClaim and has been acquired by Ansys and folded into the Workbench interface. And all the development, as I understand it, is going to be focused on SpaceClaim, and it's a really nifty tool, and I'm just learning it myself, and Design Modeler is frozen. So there's a compelling reason to go to SpaceClaim, and so what I'm doing is updating the geometry step videos and recreating them in version 18.2 using SpaceClaim. I had a long call with an ANSYS engineer to show me how to do things right in SpaceClaim so I can teach you the right way to do things rather than some kind of hacky way. And I'm really excited about it because it's very easy to use and it's very powerful, for instance, for cleaning up CAD geometries. Now, in terms of the rest of the videos, the meshing, the model setup, and so on, there's not much difference between 16.2 and 18.2. So those videos use, are the original ones from 16.2. This means that as you're going through the course, you will see some videos, mostly in the geometry step in 18.2, and then the rest are going to be in 16.2. And it's, we are engineers, so we know how to improvise, and that should work well. And if there are any changes in the other videos in meshing and so on in 18.2, we will make a note of it. The changes are minor, so we'll make a note of it by putting in text or links in the video itself. So also watch out for those. Let's specify the domain for our boundary value problem. And if I go to a slide from the pre-analysis, we saw that the domain was a rectangle of width 1 and height 2. This particular figure is not to scale. So let's input that rectangle into ANSYS. I can start ANSYS either over here. I can click on the Windows icon and go into the particular version that I want, 18.2 in this case. Or I could go into the search space and type in Workbench. And I'll start Workbench 18.2. That starts ANSYS Workbench, so you'll have to twiddle your thumbs a bit. And here you see on the left, you have lots of analysis systems. And you can think of these analysis systems as giving you access to solvers that will solve common types of mathematical models that arise in engineering. In our case, we will use the steady state thermal analysis system. So I will click on it and drag it into the project page. And that analysis system solves the steady version of the conduction equation, which is what we have. And I'll leave the default name here. Right click on geometry and go to properties first. Okay. And if I drag this here and set analysis type to 2D, and because we have a 2D problem, and ANSYS now knows that your temperature varies only in X and Y, so it's knocked off the dependence on Z because this is 2D. And also it knows that it's turned down, it knows that the equation that I want to solve is K d squared T dx squared plus partial d squared T dy squared plus Q, you can have a heat generation term, is equal to 0. And Q is 0 by default. And if you compare that to what we have over here, it's the same. And we have to, and in this case, actually, the value of K doesn't matter. By default, it'll use K for structural steel, which we will change later. Okay? So you see, with a couple of clicks, it already knows what's the governing equation you want to solve. So I will exit out of here and then right click on geometry, and you see there are two geometry engines, SpaceClaim and Design Modeler, like I mentioned previously. And you can also import a geometry from another CAD software such as SolidWorks or Inventor. And I'll say hi to Design Modeler since it's an old friend, but I will go to SpaceClaim. I'll click close here. You see there's a link to tutorials and so on that might be useful. And I want to sketch the rectangle, so I will go into the sketch mode. So I'll come down here, and I will select the option to select a sketch plane. And then when I do that, as I move the cursor, you see, as I move it to quote unquote back, it chooses the XY plane. If I move it here, it chooses the YZ. I want the XY plane, so make sure you select that. And then say plan view. So you're looking at the sketch. And then I want to sketch a rectangle. So you have the sketch toolbar here. So I'll go in and sketch a rectangle and hover around. Somewhere over here it says snapping to curve center, and you'll see that over here. So make sure you get the snapping to curve center, which means that the lower left corner of the rectangle will be at the origin. And then draw a rectangle. And you see now the dimensions are in millimeters by default, and I want it in meters. So what I'll do is I will click escape out of here, and I'll undo. Okay. And I'll go and I can go to File, Space Claim Options, go to Units, set the length to meters, and click on OK. And then if that's still selected, so I'll say snapping to curve center, and now you see the dimensions are in meters. And if I press down the space bar, it'll freeze the sketch. And let me input the dimensions I want. So I want a width of 1. So I'll enter 1 and hit the tab key, and I will enter 1 for the other dimension. So you can use the tab key to switch between the dimensions that you can enter. And then I will say, actually, that's not right. I want 2. Okay, and then I'll come into the 3D mode, and I have my surface, and I can say zoom, extends, and you can play around with the zoom and so on, and I have the surface that I want. So I will exit Space Claim. And you see I have a tick mark in geometry, and that's a good sign. Next, I'll show you how to save the project, and you can do this in a couple of ways. In the meshing step, we don't affect the mathematical model, but we give the solver some key information about how to implement the numerical solution to that mathematical model. Let's take a look at what that information is that we're giving the solver. If I highlight mesh in the tree and go to statistics, okay, first I see that there are 32 elements. I said 4 elements along here and 8 elements along there, so 4 times 8 is 32, so that's no surprise. And there are 121 nodes. That is, the solver now knows that it needs to calculate the temperature values at 121 locations. So we've given it the selected locations at which to calculate the temperature. And we can see what those locations are. Let me zoom in here using the right mouse button, and let me translate it. And I'll go here and I'll say select mesh. And then if I and make sure that the vertex, so I can select elements, which will select this, or I can select the nodes using this option, and then I will just drag it over these locations. Okay, so the corners and the midsides. So you see that it's it's going to calculate the temperature at the corners, but it's also going to calculate the temperature at the mid-sides. This means that when it writes interpolation in this direction, it can use a second order interpolation. When it writes interpolation in this direction, it can use a second order interpolation. So we have second order interpolation in two directions, and so it's going to use the second order interpolation, and we can confirm that when we actually get the solution and see what element type it's used. And we also given it information about what's called connectivity. For instance, when it writes the algebraic equation for that node, which nodal temperature values will be involved. So that algebraic equation will connect that node to all the nodes that are connected to the elements attached to that node, as we saw. So let me mark those out. So when it writes the algebraic equation at that node, it's going to involve, you look at all the elements that are attached to that node, and then you look at all the nodes that are attached to each of those elements. So all these nodes, all these nodal temperatures will be involved in that algebraic equation. Similarly, these nodal temperatures, and so on. So there are ones down here that you can't really see. So there are a lot of temperature values that will be involved when it writes the algebraic equation at any particular nodes. So as you can imagine, there is a lot of bookkeeping, which we are glad that the answer solver is going to take care of for us. Let's move on to completing the definition of the setup of the mathematical model, and then we'll get the solver to solve it. In the meshing step, we will divide the domain into nodes and elements. And in the process, we are going to mark out the selected locations at which we want the answer solver to calculate the temperatures. Go to the project page and double-click on Model. This brings up Answers Mechanical. After a little bit of hesitation, Answers Mechanical comes up, so we can specify the mesh here, and we can also specify boundary conditions and so on. So let's go to, let's highlight mesh. And I usually like to throw a default mesh on it. Sometimes it doesn't work for very complex geometries, but usually it works. And then tweak that default mesh to get a more suitable mesh. So highlight mesh and say update. And that gives me the default mesh, and I'm going to turn off the triad here so I can and I can turn off the ruler if I want under view. I'll keep the ruler for now. And I see a little bit of jaggedness in these lines. I'm not sure, if I zoom in here using the right mouse button, I'm not sure if this is an artifact of the graphics display, or it's actually a little bit, it's not exactly horizontal. And for regular geometry, you can ask it to give you a regular mesh, and you do that by putting in mesh control and say face meshing. This used to be called map face mesh in previous versions. It's the same thing. And I'm going to, so I need to have the face selection filter selected so that I can select in this face or area, and then come here and say apply. And let me zoom out here. Okay, and if I look and then I say update the mesh, and that seems more regular. And face meshing will work, only for simpler geometries. And if you have something a little bit more complicated, you can give it some guidance, on trying to get a regular mesh. And I also want to control the number of elements that I want. And I'll say I want 4 elements along there and 8 elements along there. Essentially, I want each element, each edge length to be 0.25 meters. So I'll go to mesh control and I'll say sizing. And I can scope the sizing to, I can put the sizing on lines, I can put it on areas, I'll put it on areas. So I'll click on that and say apply. And for element size, I will say 0.25 meters and double check your units here. And if you need to change the units, this is where you change it. And then update the mesh. That didn't seem to change anything. That's because in the face sizing, I have a soft setting, and the solver just took it, or the mesher just took it as, as guidance. And this is what you typically do when you have complex geometries. You can just give it some guidance on what kind of size, and then it'll adjust it according to the geometry. But for simple geometries, we want to tell the mesher, hey, don't mess with my setting. Take it as a hard setting. So I'll take that as a hard setting, and then I will update the mesh. And if I go and look at the mesh, now I see I have 4 elements along here. So it's imposed that that sizing that I gave it over here. But when I turned on the hard setting, and I have eight elements along here. And here I have 2 messages. So if I click on that, and I can click on these warnings, and it's good to take warnings seriously, otherwise they can come back to bite you in uncomfortable places. And if I double click on it, it says some element sizes are larger than the global maximum size. That's because I have this advanced size function selected. So if I go under sizing, mesh sizing, and I see the advanced size function is turned on, and and it has some maximum size over here that is being violated by our sizing. And again, advanced size function, you want it for complex geometry. For simple geometries, you can just turn it off. So when I turn it off and I update the mesh, I'll see I don't get the warning anymore. So now we have the mesh that we need, and let's next consider the number of algebraic equations that we have told the solver to generate. Let's complete the definition of the mathematical model. If I go back to a PowerPoint slide from earlier that shows the governing equations and boundary conditions, we can see the entire mathematical model, and ANSYS knows that that's the governing equation we want to solve, because we have set it to, we have dragged steady state thermal, and we have set the analysis type to 2D under geometry. So that's turned on, and it's using K for structural steel by default, but K doesn't matter in the governing equation. So I'll leave K alone for now. And we have the domain, and let's the only thing we need to specify are the boundary conditions. Let's start with the bottom boundary condition, the isothermal boundary condition. So I'll go into mechanical. I'll do some tidying up. I will say zoom to fit, and I will say select geometry, and make sure the project is saved. Okay, and then highlight steady state thermal, and it gives you the boundary conditions that you can specify, and select temperature. And it needs to be set to 1 degree Celsius, and I need to set it on a line, so select the edge selection filter here, select the line, and say apply, and set it to 1 degree Celsius. These two are insulated boundaries, so there can be no heat transfer perpendicular to the boundary, and that's a default. So I don't need to go in and do anything at those boundaries. I mean, I could go and say perfectly insulated, but that's a default, so I don't need to do anything there. And at the right boundary, I have a convection boundary condition, so I can select the boundary and then select the boundary condition, or vice versa. So I'll select the boundary and select convection. The film coefficient is h, which is set equal to bi, and bi is the BO number is 5 in our case. And make sure that the units are metric. Okay, in metric you have 5, and then ambient temperature is T infinity that we need to set to 0 to match our non-dimensional boundary value problem. So that's 0. And then in this boundary condition, there's also another constant appearing k, and k matters here. It doesn't matter in the governing equations, but it matters here. So let's give it k, and k it gets, from here. So if I go to geometry and highlight surface body, it says the material assignment is steel. So it's going to use the value of steel for k, which is not right. So let's go and specify a new material. So I'll go to the project page and double click on engineering data. Okay, that opens a new tab, and click here and say add a new material. I can give it whatever name. I'll call it Go Big Red for Big Red Cornell, and enter. And I want to give it an isotropic thermal conductivity. That is, the thermal conductivity is the same in all directions. And that, and then I can specify K, which is 1 in SI units. And you've got to be careful about units, and again make sure that it's set to metric. And then I can go back to the project page, and it says, hey, I get this symbol here. It says something upstream has changed. So I'll right click and say refresh, and that'll bring in the new material property here, and I'll do that over here too. So now it's brought in the new material property, and if I go to mechanical now, and under assignment I'll get Go Big Red. So I'll pick that, and if I bring back the PowerPoint, now it has the right value of K. And I will save the project. Okay, so at this point the governing equation is defined, the domain is defined, and the boundary conditions are defined, and we can get the answer solver to generate the algebraic equations and solve the mathematical model numerically. That's what we will do next. Now that we have completed the definition of the mathematical model within ANSYS, let's get the solver to solve it for us numerically by generating the algebraic equations on the mesh that we gave it, and then solving those algebraic equations. Go into mechanical and click solve, and it says solving the mathematical model, and it's done the numerical solution. And let me save the project. It's hiding quite a bit from us, so let's think through what happened under the hood. And for that, I'll go back to a slide from the big ideas and pre-analysis, and let me annotate my ANSYS model. The first step is to assign the temperature values for the nodes at which we have an essential boundary condition. So we have these nodes, so we have the corner nodes here, and then we also have the midside nodes. So it'll assign the temperature boundary condition for these 9 values. So they will be set, the temperature there will be set to 1 degree C. And you can see that, that boundary condition, the essential boundary condition, will be satisfied exactly. Then it needs to generate the algebraic equations at all the other nodes. So at an interior node like that, it'll, the algebraic equation will connect the nodes connected to all these elements. And then the right hand side comes from the heat generation, but we haven't turned on heat generation here, so the right hand side for those algebraic equations will be 0. And if you think about a node at the insulated boundary over here. Now for that node, the right hand side is going to come from the heat generation, which is 0, and then from the heat flux at the boundary. And in the 2D case, this is going to be a derivative in the normal direction, and again that's 0. So for these nodes, again the right hand side is 0. For nodes at the right boundary, such as this, the heat flux is not 0, so you're going to get a non-zero right hand side for those nodes. So we have 121 nodes in total. 9 temperature values will be determined from the essential boundary condition. And then there are remaining 112, which are determined by inverting 112 by 112 matrix. And that's a sparse matrix because each temperature value is related only to its immediate neighbors. So this temperature value won't be related to all of these nodal temperatures. And it's inverted that matrix, and now we have all 121 temperature values. We'll do the step 3 later on when we go to check the energy balance. Now that we have all 121 temperature values, let's get ANSYS to do the post-processing for us. I'll show you how you can probe the temperature at a particular point and get the exact value there based on the interpolation. And first, what you need to do is create a coordinate system, and then one can probe at the origin of the coordinate system. To create a coordinate system, go under Coordinate Systems and select the face selection filter and select this face. By the way, if I highlight global coordinate system, it shows me where the global coordinate system is. So I'll go to Coordinate Systems, and what it'll do is it'll whatever face I've selected, it'll put it at the center of that face, or it could be a line even. So I said new coordinate system, and see it's put it at the center of whatever face, whatever entity actually I select. Let me right click and say rename, and I'll call that my coordinate system. And I can use this coordinate system to probe the value of the temperature right at that location. There's another way I can create the coordinate system. I'll show you that too while we are here. So I'll say new create coordinate system, and I'll say define by global coordinates, and then I can just type in the global coordinates. So I'll say at x equal to 0.5 and y equal to 1, or in fact I can also pick the entity here, but I can I'll just type in the values there, and I will rename that to be my coordinate system 2. Now come into Solution and say probe temperature, and for location I will say coordinate system, and I can give either of the coordinate systems I've created. I will pick the first one. Again, it says it's probing it over there, and I will say evaluate all results, and that tells me that the temperature there is is that value. It's about 0.28. You have to interpret this as theta. It's so you can ignore this this unit, and so theta is 0.284 over there, and you can compare that to the value you get from the analytical solution that I showed you in the pre-analysis. And if you switched the probe to the other coordinate system I created, let's see, I should go in, I think I didn't, I should say, I'll say rename coordinate system 2. And so now I should see coordinate system 2. That's better. And then it says retrieve this result. It's already in the results file. So it got that. And again, that value is the same. And I can check that against the value in the contours. So if I go to the temperature contours, I was already checking this. I show you how to delete that. So if I highlight label, highlight the label and say delete. Okay, so if I go to probe, and I can see that it's around 0.286, and if I click over here, in fact I can zoom in, it's about 0.284, and that matches with what I get from the temperature probe. And in either case, you know, it's doing is it's taking the let me see. So it's taking the underlying, you know, it's all coming from the nodal temperatures. It's just an interpolation of the nodal temperatures. And okay, that's what I wanted to show you in probing the temperature. So I'll say File, Save Project. I'll show you how to extract the temperature along a line. It's a two-step process. You need to create the line, and then you need to extract the temperature along that line. I'll go back to mechanical, and incidentally, if you want to delete that label, so just select that option, select the label, and delete. And I will draw a line along the center of the model at y equal to 1. So I'll go to Model and select Construction Geometry, and then I'll select the Path option under Construction Geometry. I'll rename the path. I'll call it y equal to 1, and you can see right now the path starts and ends at the origin. So I will say I want it to start at x equal to 0, y equal to 1, and x equal to 1, and y equal to 1. So it shows me the start and the end. And the number of sampling points, I played around with this. If I used 49, so that's a number of sampling points in between those 2 points. So the total number of sampling points is those 49 plus the 2 points at the end. And that means that each, you know, division along that line will be 1 over 50, which is a nicer number than what you would get with the default number of sampling points. Now that I have my line, I can extract the temperature along that line. So I'll highlight solution in the tree and say thermal temperature, and I'll rename this. I'll call it temperature along y equals 1. And scoping, instead of geometry, which is what we did before, I'm going to say path, and select the line that we just drew. It ANSYS calls it a path, and then say evaluate all results. That shows me that, you know, here it's that line is colored by the corresponding value of temperature, so it goes from, you know, this value around 0.35 to 0.09. And if I look, and it also gives me a graph, and this slope has to be 0 because that's an insulated boundary. That's dt dx. The slope is dt dx, and since it's a natural boundary condition, it won't satisfy exactly, but it looks like it's pretty good. And you can see here the temperature is quite a bit lower because of the convection that's happening at this boundary. And you can also look at the tabular data, and it gives you, you know, the values here. You can say right click and say select all and copy cell, and you can copy this into Excel, or you can just say export, and either text, I tend to do Excel, and you can put it in in a suitable place, on the desktop or wherever, and get that data into Excel for further plotting. And this is how, for instance, one can have a nice plot where one compares the temperature along the line between answers and the analytical result. Now that we have the temperature at the selected points from the numerical solution, let's move on to post-processing. So I'll go to mechanical. Before I do the post-processing, I wanted to show you that you can actually check what element type was used. So if I go to solution information and come here and do Control F and search for type, and I say next, 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 I have to go down a few, and I see, and that's where I want it to be, and I see that the element type is plain 77. This is a special element type to impose the convection boundary condition. It's just the details of how it gets implemented in a general purpose solver, so don't worry about that. But if you look at plain 77, you can go into the help, which I've seen students are loath to do. You can search for plain 77, and you can see that it actually has the mid-side nodes, and you can look at the order of the interpolation. That's where you can confirm what is the order of the interpolation. Okay, so let's take a look at the temperature contours. I'll highlight solution in the tree, and I'll say thermal temperature. And then I'll right click on this and say evaluate all results. I can also click on solve. I like to say evaluate all results to remind myself that that's post-processing. And that's very quick because it does not involve the inversion of the stiffness matrix. What it did was it went to get the temperature value at any arbitrary location. It's just doing an interpolation from the 8 surrounding nodal values, and that's quick, as opposed to having to invert a stiffness matrix, which tends to be the most time consuming part. And you might not see the mesh over here. You can turn the mesh on or off by selecting show elements or say no wireframe. And you can change the display. You can go from contour bands to smooth contours. That's a nice pretty plot which you might want to try to impress your boss with. Or you can go to ISO lines. Not sure why this is breaking up. It might be a video card display issue. For visualization, you need a good video card. But for our purposes, this is good enough. Okay, so let me go to smooth contours, and I can also change the color bar. So I can come in here and I can click on something, and I can increase the number of contours. I can also change these values by right clicking and saying edit, and I can play around with these. One thing to keep in mind is that these max and min you cannot change, but you can change all the other values. I'll just reset it. I'll just go here and let me see if I can get it. Okay, reset all. So it goes to the default color bar view. And I can probe the temperature. So if I highlight probe here, and I can move the probe along, and it'll tell me the corresponding temperature value. And that's in degrees Celsius. So I can see that over here it's 1, red is 1, so that's a check on my boundary condition. And if I go to a location like this and look along the horizontal line, I see that the left boundary is hotter than the right boundary. Now there's no heat leaving the left boundary, but there's heat leaving the right boundary, so that makes sense that the right boundary is colder than the left boundary, which is hotter. And one can also take a snapshot. So one can go here and say image to file, and then you can say OK, and you can save it to a PNG file, say on the desktop. You can call it, you can give it an appropriate name. I have my usual underscore. You could also use the Windows snipping tool. So if I say snip, and I can just, you know, mark out the area where I want to snip, and I can save it. I won't do that over here. So that's, you know, that's the temperature contours that comes from the interpolation. And let's take a look at the heat flux next. But before that, I'll save the project. Next, let's take a look at the heat flux. Highlight solution in the tree, thermal total heat flux. Right click and say evaluate all results. That'll give me the total heat flux. And let's visualize these as vectors, because heat flux is a vector. So I can click on that, and I will let me increase the size of the vectors, and I see I have a very high heat flow coming in here, and everything else is small compared to that. And that's that makes sense, because heat is being lost from this edge, and you know, to keep this edge at 1 degree, it's going to require that you put in a lot of heat over here. We can also visualize this as vectors of equal length. So I can select that. And then I like to use solid form for the symbols. And then I can play around with the size. And what this is doing is it's plotting an arrow at each node. I can see that if I go here and I turn on the elements. So you can see there's an arrow at each node. So at each node it's determining both components of the heat flux. Let's think about that. Let me annotate this. Heat flux is a vector, and so you have the heat flux in the x direction, which is the heat flow per unit area in the x direction. And then you have heat flux similarly in the y direction. And the x component is related to the gradient of the temperature in the x direction, and similarly for the y component. So what it's done is it's gone to the temperature interpolation, and it's differentiated it to find qx, and similarly for qy. Remember from the big ideas in FEA that when we differentiate a numerically obtained result, it's going to increase the error. So this, you know, the heat flux is going to have more error than the temperature. In fact, we will see that as we refine the mesh, this value keeps going up. So this value is in fact, I believe it'll go up in an unbounded way as you refine the mesh. And we can use this to check the boundary conditions. So here we have an isothermal boundary condition, which means that the temperature is constant along this line. That means there can be no heat flow along this line, and so the heat has to be perpendicular. So that's a check on that boundary condition. And over here it's insulated, so it can't cross that boundary. And so it's along there, and over here it's along there, and here, you know, you get something funky because at the corner you have two directions in which you cannot have heat flux, and this is a very small value, so we'll not worry too much about it. And then you can see that the heat flow, you know, heat is flowing out to the fluid over here. And you can see that, you know, though the heat flux is supposed to be 0 at these boundaries, it's actually a very small value. So as we saw, the natural boundary condition is satisfied only approximately, whereas the essential boundary condition is satisfied exactly. And we see the effect of that there. And you can save the project. Let's check the energy balance. In the big ideas in FEA, we saw that from the discrete equation, at the essential boundary condition, we were able to calculate the reaction, and that involved the heat flux at that node times the area of that phase. And that was step 3 in the finite element procedure. And so that's what we will do. We'll calculate the reactions. And here, the reaction will involve, you need an area. So for that, you need not only this length here, but you also need the dimension perpendicular to the screen, and that's given by the thickness. So if I go to surface body, and the thickness is 1 by default, so you can think of whatever reaction you'll get along here is the heat flow through that boundary per unit thickness. So let's calculate that reaction at that essential boundary condition. So I'll highlight solution in the tree, and I'll say probe reaction, and I'll pick my temperature boundary condition, and I will say this is, and I'll say evaluate all results. And that tells me that the heat flow, the net heat flow through that boundary is 1.67 watts, and the direction is into the domain, so that it's taking as positive. And it turns out, you can also get a reaction at the convection boundary condition, which we haven't talked about. Convection is a more complex boundary condition because it involves both the temperature and its gradient. So let's just use the facility in the code to calculate the reaction there. So I will highlight solution, say probe, reaction, and then pick the convection boundary condition, and say evaluate all results. And that's negative because the heat is flowing out through that boundary, as we can check with the heat flow. Under the heat flux vector, so you have heat coming in, heat going out, there's no heat crossing the other two boundaries, and there's no heat generation. So this has to balance that, and if I look at that value, that balances the heat coming in. So that's a check on the aggregate energy imbalance. We saw that doesn't mean that energy is conserved for each infinitesimal element, or it's conserved for each finite element. It just means that it's conserved in aggregate. But that's a very important check to do. Here we'll do the mesh refinement to evaluate the level of numerical error. Exit out of mechanical and go back to the project page and right-click on model and say duplicate. And that duplicates the model and everything downstream of it, but things upstream like geometry and engineering data, it's just referencing the original geometry and original engineering data. So I can't modify this geometry engineering data. I've gone and modified this, and it'll affect this as well as that. And I'll call that project mesh 2. I'll call this mesh 1. I'll use a right click on that, use capital M, and double click on model. And I'll go into mesh, and all I'll do is I will change the sizing. So the original sizing, each element edge was 0.25. So I'll use half of that. So I'll say equal to 0.25 divided by 2. Sorry. Okay, that's the value I was looking for. 0.125, and I'll say update the mesh. And since I have, if I look at the mesh, I'll have twice the number of elements in this direction and twice the number of elements in this direction. So totally I'll have 4 times the number of elements, and I can check that under mesh statistics over here. Okay, now I have 128 elements and 433 nodes. And if I click on solve, ANSYS will regenerate the algebraic equations and determine the 433 nodal temperatures, and it'll also do the post-processing that we had requested. And I can go and look at the temperature and compare that to, I can save a snapshot and compare it to the original temperature distribution. I can do the same thing for the heat flux. In fact, I can see that the heat flux at the insulated boundaries has gone down by quite a bit. So my natural boundary condition is being satisfied better and better, which is what I would expect. But I'll let you compare, the temperature contour side by side, the heat flux side by side, and also the reactions, how they change as you refine the mesh. And that brings us to the end of this this module. So I will exit out of here, and I'll say File Save, and at this point I'll say File, Archive, and I'll go back to my original archive, and I'll say Save, and I'll replace it, and I'll save my results, because in this case it's not going to give me a very big file. And if you go back to the WB, to your folder, you'll see that it's overwritten the WBPZ file, and you can save that to a flash drive or a network drive if you are on a public computer. That brings us to the end of the conduction module, and in the process we have explored some really fundamental ideas in finite element and how you implement it using ANSYS. Let's do the verification and validation. Verification is looking at whether we solved the mathematical model correctly, so it's looking at whether these steps were done right, whether we input the right mathematical model and we solved it correctly. So we will do that. And validation is looking at, is complementary to that. It's looking at whether the model we have, the mathematical model we have picked, is a right representation of the physics. And for that we need experimental data, which we don't really have over here, so we won't be doing validation. And under verification, the first thing is to do sanity checks, and we have been doing that as we've gone along, looking at temperature distribution, looking at heat flux vectors, and so on. So sanity checks we have already done. The mathematical model consists of governing equations and boundary conditions, and the boundary conditions we have checked as we have gone along. So we are pretty confident that we have, our boundary conditions and our results are consistent with the boundary condition in our mathematical model, so we have input the right boundary conditions into the tool. And then the governing equations contain, the physical principle contained in the governing equation is energy conservation or energy balance. So we can look at the results and check if the results are consistent with that physical principle, which is energy conservation. Okay, so we will check that by checking the reactions, as I talked about in the big ideas in FEA. Okay, so with those checks we can be fairly confident that we have input the right mathematical model into the tool. And in terms of the numerical error, how the tool has solved it, as we discussed in this problem, really the only thing we need to worry about is doing a mesh refinement, because it's already using the second order interpolation with the mid-side nodes. And in practice you never go to the third order interpolation. So to check the numerical error, we'll do a mesh refinement. Okay, so that's to be done. And the third aspect of verification is to check versus hand calculations, and part of our sanity checks involved checking boundary conditions via expectations of trends. So we've done that, and then here we have an exact solution to the mathematical model, and we need to check that. I'm not going to do that here, but if you come to Cornell and take a heat transfer course with Professor Luge, he might make you do that as part of the homework, because he often assigns this as the homework in his heat transfer course. So for verification, then we will do we'll check energy conservation, and we'll do a mesh refinement study.